Hi, and welcome to Module 2 of Lecture 12. Now in the previous module we went through and discussed the intuition and the usage of eigenvalues and eigenvectors in political science and social sciences more generally. Now next two modules we're going to go through and actually calculate these things. It turns out it's not so bad. A lot of the stuff makes a bunch of sense using stuff we did in the previous lecture. Just get right to it. Recall from the previous module that the eigenvalue equation, equivalent eigenvector equation, looked like this. So here's your matrix A, and here's your eigenvalue lambda, and both those apply to a particular eigenvector v, which is the same on both sides. Now we want to know first how to calculate the eigenvalue lambda. And it turns out you have to do that first in all cases. Now how do we go through and calculate the eigenvalue? Well, we can manipulate this eigenvalue equation to find a way to calculate it pretty simply. So let's do that. First, note that if you multiply the right-hand side by the identity matrix, nothing changes. The identity matrix, we call times any matrix or any vector, just returns that matrix or vector back again. So this is the exact same thing as that. No change at all. Okay, goes up. The identity matrix I times v just gives you v back again. Now, we can subtract from both sides, the right-hand side, to get you this equation. Now we note that v is right multiplying both sides, so we can distribute it, or undistribute it, I guess, to get that. And that's going to be equal to 0. I should make 0 on this side. Now, what does that mean? Well, A minus lambda I is just a matrix, right? Lambda I is a matrix, the matrix with lambdas all along the diagonal, and A is a matrix that you started with, so A minus lambda I is a different matrix. Now, what this means, if the matrix times some vector is equal to 0, what this means is that effectively, this is a linear combination of the elements of v, recall, and that means the fact that it's 0 means we can actually find a linear combination of the different elements of v, which means that this matrix over here, the columns of the matrix are not linearly independent. What that means is that, and the rows are not independent either, that means this matrix is singular. We don't have a set of linear independent rows or columns, which means the matrix A minus lambda I is singular. Well, what's true for a singular matrix? Well, for a singular matrix, the determinant of that matrix is 0. This thing is going to produce, because all the elements of A and all the elements of I are just constants, this is going to produce a polynomial in lambda. This is called the characteristic polynomial. And this whole thing is a characteristic equation. And if you solve this polynomial, all the values of lambda that solve this polynomial will be eigenvalues, will be characteristic values of the matrix. And that's the way it works. So again, you start here with the eigenvalue equation that defines the eigenvalue, multiply by I, subtract from both sides, undistribute. So far that's all pretty straightforward. And the key is noting over here that this whole equation here implies that the rows and columns of the matrix A minus lambda I are not linearly independent. If you don't remember that, go back to the previous lecture when we talked about linear independence and linear dependence. If you have a matrix made up of a bunch of linearly dependent rows and columns, that matrix will be singular. Therefore, a singular matrix has a determinant of 0. And again, if you don't remember that, go back to your previous 2 lectures. But a singular matrix with a determinant of 0 means this is true, and that gives you a characteristic equation to solve for lambda, and lambda will be the roots of the characteristic polynomial given by this determinant right here. And that's it. That's how you get the actual solution. So let's start from there. To find the eigenvalues of a matrix, all we have to do is solve for the roots of this characteristic polynomial, or equivalently solve this characteristic equation for lambda. So let's do that. Let's make up something on the fly. It might work, it might not. We'll try it. 2, 1, 3, 4. There we go. There's our matrix. Now what's lambda I? Well, lambda I is a 2 by 2 I we want. So we will have lambdas along the diagonal. Remember, multiplying by a scalar means you multiply each element by the scalar. 0 times lambda is still 0. So now a minus lambda I is going to equal what? 2 minus lambda, 1, 3, and 4 minus lambda. And this thing, the determinant of this, is going to be equal to 0. What's the determinant? Well, if you recall, the determinant of this matrix right here was AD minus BC. So the determinant of A minus lambda I, and again, if you don't remember that, go back to your previous lectures, is going to be 2 minus lambda times 4 minus lambda minus 4. That gives you 8 minus 4 lambda minus 2 lambda is minus 6 lambda plus lambda squared minus 4 equals 0. Well, that's lambda squared minus 6 lambda plus 4 equals 0. And y actually works. Then you have lambda minus, no, I'm wrong about that. Yeah, okay. So use the quadratic formula. Lambda is going to equal negative b, that's 6, plus or minus the square root of 4ac. So b squared is 36, square root of b squared minus 4ac. Minus 4ac is 4 times 4 is 16 over 2. A is just 1. So this is 3 plus or minus the square root of 20 over 2, which equals 3 plus or minus, take the 4 out of there, the square root of 5. And there are your two eigenvalues, 3 plus the square root of 5 and 3 minus the square root of 5. That's it. Those are the eigenvalues of this equation. In the book, we have a different example that carefully constructed to make it work with whole numbers, but the point is this is the eigenvalue. All you do is take a minus lambda I, which is usually pretty easy to construct. All it involves is subtracting lambdas from the diagonal elements. Take the determinant, and you're done. That's it. There's the eigenvalues. I'll attempt fade here and try one more with a 3 by 3 one. This is going to be way harder to actually make it work correctly, but we'll just show how it works in general. Let's see. 0, 1, 0. 2, 1, 1, and I don't know, 1, 1, 2. I totally made it up. This probably won't work, but we'll try it. I think there's no obvious multiplied things here. So now we know what lambda I is. So a minus lambda I is going to be negative lambda, 1, 0, 2, 1 minus lambda, 1, 1, 1, and 2 minus lambda. There you go. What's the determinant of that? We have to expand this out. We can expand over any row or column we want. Let's use the first row because there's still a 0 there. So it's going to be, so we can do this correctly on the fly. That's negative lambda out front times the determinant of the matrix gotten by removing this and this. That's 1 minus lambda times 2 minus lambda minus 1. Now we use this second one. So that's going to be, it's minus 1 because it's the first row, second column. 1 plus 2 is 3. Negative 1 to the third is negative 1. Again, if you don't remember that, go back to how to calculate determinants in your previous lecture. Now we take this row and this column gone, so it's 2 times 2 minus lambda minus 1. There you go. Okay. And that's 0, so we get rid of it. Plus 0. Okay. now we have a big mess. And you can tell it gets much harder to calculate eigenvalues with bigger matrices quickly. So it's difficult to find the one quickly that just works on the fly. But we can multiply this thing out. We get, let's see, negative lambda. Do this thing inside first. That's 2 minus 3 lambda plus lambda squared minus 1 minus, that's going to be 4 minus 2 lambda minus 1. That's going to equal, let's see, we got lambda, negative lambda cubed. Negative doesn't matter, to go away. Negative lambda cubed minus plus 3 lambda squared. 2 minus 1 is 1, so that's minus lambda. Then that'd be 4 minus 1 is 3, so that's minus 3. That's plus 2 lambda. So finally we get negative lambda to the third plus 3 lambda squared. And then plus lambda minus 3 equals 0. And to make it life easier, get rid of the negative sign. So you have negative lambda to the third minus 3 lambda squared minus lambda plus 3 equals 0. And there you go. Now this may simplify. I don't know offhand what it is, but you know what? This particular lecture is not on finding individual solutions to cubic equations. It's on finding eigenvalues. So we're done. The 3 eigenvalues to this equation will be the solutions. Sorry, the 3 eigenvalues to this matrix A will be the solutions to this equation right here. You can try to factor that. Maybe it factors, maybe it doesn't. You can use other techniques. You can use a computer, whatever you want. But that's how you find eigenvalues. As you can tell, eigenvalues for 2 by 2 matrices are pretty straightforward. For 3 by 3 become a little trickier to find the good one that works well. In the book, there's an example that was carefully chosen to work exactly right, to be easily factorable. This one was not carefully chosen to do that. But there you go. This gives you a sense of how to go about doing this. This gives you how to calculate eigenvalues. In practice, oftentimes we calculate eigenvalues using some kind of computer program that'll do it for you. And oftentimes when you actually want to calculate eigenvalues, all you actually care about is are they positive or negative. And in that case, what you do is just graph this thing and see if the roots, the parts squared across 0, are all positive or negative. There you go. That's how to calculate eigenvalues. In the next module, we'll discuss how to calculate eigenvectors. Thank you very much.